All right, so this is the divergence theorem. So just a quick reminder, if we go, what was that divergence portion about, right? So the divergence said if we can do the line integral of a vector field, that equal to the double integral over a region D of the divergence of f dA. Okay. Now, that was for, right, this is in 1 to 2. So the process is, well, what if I just do an extra one? So what if I go to higher dimensions, to 3 dimensions? And then we actually could do that the same way we can here. So how that works is, all we do if we take the integral of both sides, we end up getting the double integral here, which now this becomes a surface. And we take over here, we get the triple integral. And now, because this is not a region, it's a sphere now, right? It's in 3 dimensions, and now we return the volume. This actually gets the same thing. So you could think of the divergence theorem is just going up one dimension, and that's actually our divergence theorem there. Is let E be a solid region, and let S be a boundary surface of E, given with a positive orientation. Let F be a vector field whose components of functions have continuous derivatives, so you could take the partial derivatives of it. So therefore, we have this portion here. Now the key thing is, remember, this is a surface integral. So we're taking a surface integral in R2, this is R2, and we're using this into a region in R3. Okay. Which is pretty interesting. So remember, like this is portion here, we go from just a line, just like, straight line, or curved line, into a 2-dimensional plane. Same thing applies here. We're getting something in 2 dimensions and convert it into 3 dimensions. Okay? That's our way when it comes to our divergence theorem. So again, it's another way to make surface integrals easier to simplify and to actually solve. Okay? Now, this is so important when it comes to physics and engineering. This is what is called the flux of a vector field across the boundary of a surface. Okay, so it's more proper way of saying is finding the flux of the vector field. Okay, so let's try an example so you can see how this will work out. So find the flux of the vector field, given that f is equal to that over the sphere x plus y squared c squared equals 3. Now, since we have x squared plus y squared plus z squared equals 3, we know we're going to have to convert everything to spherical coordinates. Okay. Now, before we get there, we'll just do this process. So find the divergence of f. So remember, divergence is just the vector field dot product its gradient. So all we're really going to do is take the partial derivative with respect to x, y, z, and just add them all up. So derivative with respect to x is 0, derivative with respect to y is 1, and the derivative with respect to z is 0. So this ends up being just 1. So we're just taking the triple integral of just 1 dv. So just pretty much finding the volume of the sphere with radius 1, basically. Well, we'll talk about the radius in a little bit. Okay, so if we want to convert this to spherical coordinates, so that we know that phi squared is equal to 3, so therefore rho is bounded between, rho bounded between 0 and radical 3. It's a sphere, so we know that phi goes from 0 to pi, and theta, it goes from 0 to 2 pi. Okay. So this is going to be the triple integral from 0 to 2 pi, 0 to pi, and then 0 to radical 3. And our conversion is rho squared sine phi d rho d phi d theta. And I'm purposely not putting in phi because I technically know what it is, and just for there's a reason for that. Okay. So integrating respect to first row, so that's just going to be root of 3 sine phi, because this is a constant, evaluate at 0 and radical 3. 0 goes away, so plug it in. That gives you 3 radical 3. Those cancel, so you just get radical 3 sine of phi, d phi, d theta. All right, so integral of sine is negative cosine. So this is going to be minus radical 3 cosine phi. Evaluate at 0 and pi. Okay, so cosine of pi is negative 1. Cosine of 0 is 1. So this ends up being 2 radical 3, because this ends up being positive. Negative 2, and negatives cancel when you multiply them. So lastly is just going to be that, which is just, itself times it, so you get 4 radical 3 as your answer. Now there's a reason why I didn't put that at the very beginning, so I want to show you guys. If you guys remember, the volume of a sphere is equal to 4/3 pi r to the third. So if I would just plug in what the radius is in the beginning, which is radical 3 into here, I get exactly that. So essentially, this is a type of proof, because if I just put this to, let's say, r in general, r squared in general, this gives you a proof how to find the volume of a sphere, because it's exactly the way to do it. So if I just plug that to r, you would get exactly the volume of a sphere. So it just shows you the flux of getting the flux of a vector field over, in this case, a surface, actually gives you the volume itself, right? And it gives you the general volume of any type of sphere, sorry. So, this is another algebraic approach to, find the volume of stuff without geometrically doing it, which is pretty cool, right, when it comes to that. So let's try one more example to get you guys more comfortable with flux. So find the surface integral f ds, where our vector field is that, and the surface is the region E bounded by this cylinder z equaling 1 minus x squared, and the planes z equals 0, y equals 0, and y plus z equals 2. Okay, so for this one, let's break some stuff down, what's going on. All right, so we're going to use the same thing we did last time. We're going to convert this to the triple integral of the divergence of f dv. Okay, but this time we don't actually have to convert it. We'll just go straight from its portions, and I'll show you why in a little bit. But first, again, let's find the divergence of f. So again, each partial add up together. So do with respect to x, do with respect to y. This is all gone because there's no y's there. And then do with respect to z is 0. There's nothing there. So now, notice, find the triple integral of 3y is so much easier than trying to find the double derivative, right, of this whole thing. Because now we have to parameterize it, all that fun stuff, and hopefully, the integral is nice to deal with. Okay? And this actually is pretty nice, because if we look at our bounds, we know z is bounded between 0 and that. We know y is bounded between 0, and if I solve for y here, 2 minus z, so 2 minus z. Now let's look at x. So if I plug in 0 in for x, 0 in for z here, I get 0 is equal to 1 minus x squared. So bring it over, and then gets 1. Because it has to be above the plane, because it has to be z equals 0, y equals 0. Okay. So now we just plug it in and see what we get. Actually, what am I doing? X could be anything I want, so I got negative 1 to 1. Z, yeah. X could go up or down, yeah. So plug it in, so it becomes Okay, bounds of integration, so I gotta be careful here. So I'm gonna do x last, because that's the numbers, and then what's dependent on x? It's gonna be z. And then first dy of that. Okay. So integrating this, plug it in, so it gives me, bring this just on the outside, of 2 minus z squared. We're evaluating, oh, plug-in 0 goes away, so plug in this. So there. Okay, so this is a u substitution. I could bring this on the outside, so let u equal all of this on the inside. So therefore du is negative 1 dz. So I'm just going to have a negative on the outside. Integral of z squared is just z third over 2, over 3. So 3's cancel, you get that negative. So this ends up being negative 1/2 of the third power. Ooh, not done yet, right? Evaluate at 2 minus z to the third power. Evaluate it at 0 and 1 minus x squared. So plugging all this in, and if plug in 0, you get an actual number, you get negative 8. So 8 itself, so you plug this in first, you get 2 minus 1 plus x squared to the third power minus 8. So this ends up being 1. Okay. So now if I went ahead and just FOIL this, so it's 1 plus x squared to the third power. And once you FOIL it out, this is what you get. That's included, I put the 1/2 in there, and it gives us roughly this. Put this one here. Oh, minus, these are all minuses. And then, maybe I should have just kept the left. I know what I'll do. I'll just leave this on the outside to make it easier to look at. I'll keep that on the outside. And then this is supposed to be a plus 1. Minus 8 gives you negative 7. There we go. Just make it life a little easier. So these aren't here, they're on the outside. So integrating this, and then plugging in 1 and negative 1, and then negative 1/2 is on the outside there. So plugging in 1, again, it's negative 1 on the outside. 1/7 plus 3/5 plus 1 minus 7, minus plug in negative 1, gives us that. Okay. So I get something approximately positive 4.7. All right, so little applications of what the divergence comes into play. So these are the two major ones when it comes to electric charge over closed surfaces. So it shows you, where the electric charge is flowing through and how strong it actually is. So force fields and all that. So big thing when it comes to magnetism. So that's the easiest example we can have ourselves. if you put a magnet together, you obviously you can't see the naked eye, but you could tell what's the vector fields are going around it. And you can see the charge of it itself. So it goes into chemistry as well. And then the other one is the big one is the fluid flow, the rate of change of it. Now this is a nice one because this type of divergence theorem tells us one of the biggest thing is the flow that towards going towards or away from the origin and how fast it actually is. So lots of interesting stuff how divergence theorem goes into play and how to end this section. But a couple little examples so you can see how the applications are actually done in the real world.